the quality of our DEMs. This is going to depend on something that I've already spoken about, obviously the support size. Is it small enough? The area that we are actually surveying when we create the data, not the raster itself, not the tin, but the actual measurements that are being made, are they of a small enough area for our needs? And this is going to vary depending on what we want to do. The elevation that is measured at any particular point, it's not we end up with a point when we do our measurements, is based on some area. And is that area small enough or of the correct size, a reasonable size for our analysis? If it's too large, we don't know what's happening within that area. It may be a very correct measurement of the generalized elevation in that particular area, but it's not going to give us the details that we need. Then we need to take that over to the raster, say, and is the cell size appropriate? Is it small enough, appropriate to the support? We're not allowed to sample down to or sample up to a higher resolution. That's not allowed. So the connection between the cell size and the support is essential here. We need to make sure they're small enough, but the cell size itself also needs to be appropriate for the calculations that we are doing. It should be no larger than is necessary. We may need to resample to a larger cell size for the calculation to run in a reasonable time on our computer. This is true for larger data sets. And obviously this becomes less and less of a problem with faster and faster computers with more and more memory, but even so, it's something we need to consider. And this obviously connects, or both of these points connect to things missing in the data, features that are of essence. This is particularly it's important in lots of areas, but we can exemplify this in, say, hydrology, whereby a river channel or a rivulet, some small feature might exist or not exist, depending on whether we've gathered enough data of the right support, the right density, the right size, in order to capture that feature. Or it might exist in one place and then stop in our data set, to then turn up again later on, whereas in actual fact it is a continuous feature that's just not being captured by our data. We can also introduce artifacts, and we will look more closely at what artifacts are later on in this lecture. There's things that aren't there. For instance, this breakage in a feature. We have a linear feature that exists across an area that suddenly stops existing because our data was not of a high enough resolution to gather it. And as we've also seen, we have the effect of pits and peaks, kriging, and it's over smoothing. Everything looks nice and smooth, but it shouldn't look like that. Or with the triangulated irregular network, we have this kind of this faceted look, where everything was made of triangles and they were clearly visible in the data set. Also an indication that our data density is not high enough for our purposes at that resolution, at that distance, so to speak, that we're looking at the ground from. So if we then see what happens when we start doing analysis, the relationship between quality and analysis. Primary analyses of elevation, we tend to be talking about things like slope. The degree or percent, so degree is simply the degrees that you can think of, 0 being flat and then 90 degrees being straight up. Percent can confuse the novice, and this is simply the relationship between the distance along ground and the elevation change. So if the elevation change is as much as the distance along ground, that's 100%. So 100% is 45 degrees, so it can be a little confusing. Aspect is the direction of the slope. Question is whether that should be a primary or a secondary analysis, but that's a good point, because without slope there is no aspect, but we'll leave it at this at this point. So aspect obviously is going to give you to begin with a bearing going from 0 to 360 degrees, which means that you have 0 and 360, which represent the same thing, or let's say 359 and 1 are separated by 2 degrees, actually. So when we want to represent these and put them on a map, we have a small problem. Either we have to do some weird classing of data, or we can actually just decide to use the sine or the cosine of the bearing to give us the north-southiness or the east-westiness of the area, if that's what we're interested in. So let's quickly look here. We have a rather strange table there of elevations. They're the wrong way around, but let's just go with that. So here we have that same area again with our esker and the river running through it there. And the white colour here is a high elevation passing through the dark colours and then down to the lowest elevation being the blues. And when we look at the slope, so if we go back, we can see that this would appear to be a fairly rapid change here, and that's borne out by the red colours here where we have a high slope. So rapid changes in elevation. And we can see those as well in the river here, which feels fairly obvious in that we have a river and then it suddenly changes. We have steep banks and then the river bottom. So that doesn't feel terribly wrong. That feels like a pretty correct representation. And we can even see up here on the top of the esker, we get these blue colours again with very little slope because we're at the top of the ridge. But then when we look at aspect, which way is it facing, we get this this division between the reds and the blues in this case that I've been using, where things suddenly flip rather than gradually transition into a new hue or shade because of this issue with going from just a 2 degrees change puts you all the way around there again. So we can use this, we can use this thing with, for example, the cosine of the aspect. And that gives us our degree of northiness and southiness. Secondary analyses, slightly more complex. For example, Viewshed for noise propagation, not perfect obviously, and wind speed, whereby we're assuming that something that's in the way is going to slow these things down or stop them, perhaps even completely. Of course, they can refract and bounce around, but generally speaking, these are used quite well in this sense. So what does this show us? Well, if we're standing here, we can't see beyond the esker. All that is invisible to us, even though it's at the same elevation. This ridge is blocking it. And similarly here, we have a slight area of high ground, which means that we can't see just below that high ground on the opposite side of it, but then we can see the area beyond that because it's not high enough to block our view of the distance. Simple viewshed analysis. Things like cut and fill for volume calculations. How much is there? How deep is a lake, or how much do we need to mine out or refill? Building roads, this is quite handy. So cut and fill, and we take that mass, we cut it out, and we lay it up there to build our road. So here we have a drainage ditch. This might even help with reducing downslope pressures as well, so that we avoid landslides. Although we've increased them here by adding more weight there. So ups and downs. Or secondary analysis, hydrologic models, which we've already looked at in previous courses. For example, the D8. Where we're looking at flow direction through this, which is not the only hydrological model, but we're probably not going to be going beyond that anytime soon. Obviously, we can, if you're a more advanced user, you can use things like head graphs and what have you. But for us, simple D8 analysis of the topography will give us a reasonably good approximation of flow direction. We can also do a more, should we say, manual interpretation of the area of the DEM for geomorphology. There are tools such as topographic wetness index, topographic position index, things like this, which will try and calculate the degree of being up on a ridge or a mountaintop that a particular point is. They're quite complex calculations. or very time-consuming computations. They can take a while for the computer to run through the entire DEM and calculate these things. Whereas we can actually just do manually our own little survey here. We've got the elevation model in the background again, overlain with a hillshade, slightly transparent hillshade, which brings out certain details. Hillshades are great for visualization, but also for our own manual interpretation. And we can see this esker that's kind of been broken up, partly by being dug out in certain places. This is an excavation of the esker, and other places has been washed out by the river some point prior to humans turning up here in this area. But we also have other topographic features, and we can even see here a road running through rivers. We can work out roughly what's going on in this area, make some interpretation of what's going on using the relative relief in this. Other secondary analyses, I mean, this might even come down to being tertiary analyses now, looking at erosion and sedimentation, mass transport through the landscape, usually requiring some extra information as well as not just the DEM. But we can see where things are going to be eroded from and where they're going to end up being sedimented out. This obviously is gradient dependent as well as soil type dependent. So we're looking very much at the gradient of the surface.